Welcome to The Explainer. Today, we're going to dive into a concept that's right at the heart of building systems that can handle massive scale, database sharding. We're going to break down how you can take that explosive growth, which can be a huge problem, and turn it into your biggest superpower.
So let's kick things off with a problem that, let's be honest, is a dream problem to have. Your app is a total hit. Users are pouring in, it's growing faster than you ever imagined. But your database, that single trusty database, it just can't keep up.
And this is what that pressure really looks like in practice. The amount of data you have to store is just exploding. The number of queries hitting your database every second skyrockets, and you hit this hard physical limit on how much new data you can even write. All of a sudden, your reliable database has become the single point of failure for your entire system.
So here's the game plan. We'll start by digging into that scaling bottleneck. Then we'll compare sharding with another key concept, replication. After that, we'll get into the different strategies for sharding, talk about the really tricky challenges, and then wrap it all up with a real-world architecture.
All right, first up, the scaling bottleneck. Let's really nail down the problem we're trying to solve here.
At its heart, sharding is basically this idea of taking that one giant, overwhelmed database and just breaking it apart. You split it into these smaller, more manageable, and much faster pieces that we call shards. Each shard gets its own machine, and it only has to worry about a small piece of the total data and traffic.
Okay, moving on. This next part is super important. Sharding versus replication. People mix these up all the time.
Okay, so here's the absolute key difference you got to get. Sharding is all about splitting your data up. Why? To scale your ability to write new information and just store more of it. Replication, on the other hand, is about making identical copies of your data. This is for scaling your ability to read information and, crucially, to make sure your system stays online if a machine goes down. Any real-world system, it's going to use both.
All right, section 3. This is where the real fun begins. Choosing a sharding strategy. Think of this as the architect's playbook, and it all, and I mean all, starts with something called the shard key.
And look, that's not being dramatic at all. The shard key is the rule, the logic, that decides which piece of data goes on which shard. If you mess this up at the beginning, you are literally signing up for a future filled with operational pain, terrible performance, and fixes that are just incredibly complex to implement.
So, strategy number 1, the most straightforward way to do this is called range-based sharding, and it's exactly what it sounds like. You split your data based on a range of values. You could say, user IDs 1 through 1 million, they go on shard 1. The next million, they go on shard 2. Simple as that.
So the trade-off here is pretty classic, right? On one hand, the logic is super simple to understand, and if you need to find a range of users, it's incredibly efficient. But, and this is a huge but, it has this massive potential flaw. Hotspots. Just imagine you launch in a new country and 1 million new users sign up at once. They would all slam the very last shard, completely overwhelming it, while all your other shards are just sitting there, bored.
So to get around that whole hotspot nightmare, we have a much more common and, frankly, robust approach, hash-based sharding. With this, instead of a simple range, you take your shard key, like the user ID, and you run it through a hash function. The number that comes out of that function tells you exactly which shard metadata should live on. And boom, here's the next big trade-off. What's so great about this is that the hashing gives you this beautiful, even, almost random distribution of data. It's fantastic for avoiding hotspots, but the price you pay is that those simple range queries, they become a nightmare. Finding users 1 through 100 might mean you have to go ask every single shard in your entire system.
So it doesn't matter which strategy you pick. A good shard key absolutely has to tick these boxes. It needs to spread the load evenly across your machines. It has to make sense for how your application actually asks for data. And maybe most importantly, you want to minimize any operations that have to go talk to more than one shard at a time.
All right, section 4. Look, sharding is incredibly powerful, but let's be real, it's not a magic bullet. It introduces its own set of pretty gnarly challenges. Let's talk about those hidden hurdles.
So, this is probably one of the single biggest headaches with sharding. If your query has the shard key in it, like find user 123, it's easy. You know exactly which machine to talk to. But what if it doesn't? How would you find the top 10 most popular posts across your entire platform when you know those posts are scattered everywhere?
Well, the answer is this pretty clunky and often expensive process called a scatter-gather query.
Your system literally has to scatter the query out to every single shard, then it has to wait for all of them to respond with their local top 10. And then finally, it has to gather all those lists together to figure out the true global top 10. It works, but it can be really slow. A huge part of designing a good sharded system is trying to avoid these kinds of queries.
And then there's the other monster in the closet, rebalancing. Your app is going to keep growing, right? So eventually you're going to need to add more shards. But it's not just plugging in a new server. Adding a shard can change the rules of where data is supposed to live. This can mean you have to move massive amounts of data. We're talking terabytes, maybe petabytes, between machines, all while keeping the entire system up and running. It's a huge operational challenge.
Okay, so we've talked about the theory, the strategies, the problems. Now let's put it all together and see what this actually looks like in the real world.
So this is basically the blueprint for a production-ready system. First thing you notice, the client isn't talking straight to the databases. No way. It talks to a smart router or a proxy layer. That router looks at every request, uses the sharding logic to figure out exactly which shard has the data, and sends the request to the right place. And you can also see that each shard isn't just one machine. It's its own little cluster with replicas for failover and read scaling. This is where sharding and replication come together beautifully.
And look, this isn't just some textbook theory, right? This is the core architecture that powers some of the absolute biggest systems on the planet. From the way Instagram stores all our user data to how Facebook manages that ridiculously massive social graph, sharding is the secret sauce that makes their scale even possible.
So when you boil it all down, it comes to this fundamental trade-off, this one big idea. Sharding gives you almost limitless horizontal scale and incredible performance. But that power comes at a cost, and that cost is a huge increase in complexity. Things that used to be simple, like queries and transactions, suddenly become much, much harder.
And that really brings us to our final takeaway. Sharding is how you partition data to scale your writes. It lets you break past the limits of a single machine, but it introduces all this new complexity. And in the real world, you'll always combine it with replication. That's the whole story. The only question left is, what problem are you going to solve with it?